Hi, I'm Barry Williams, and this week I'm looking at polygenic genome editing using type 2 diabetes as my case study. And most people think of genetic disease as one broken gene causing one clear problem. And that model does work for something like cystic fibrosis, for instance. But most of the diseases that actually kill people, meaning heart disease, type 2 diabetes, schizophrenia, don't work that way. They come from hundreds or even thousands of genetic variants, each contributing a tiny nudge in risk. This week is about what happens when we try to edit that whole picture at once and not just one gene. With a monogenic disease, you can usually point to one gene and say, that's the problem. Polygenic disease doesn't work like that. Type 2 diabetes comes from hundreds or thousands of variants scattered across the genome, each one nudging risk up or down by a tiny amount. No single variant is the cause. It's the sum of all of them together combined with diet, weight, and activity level that determines who actually develops the disease. A polygenic risk score is basically a weighted sum. Researchers run genome-wide association studies comparing large groups of people with and without type 2 diabetes, figure out which variants show up more often in the people who have it, and assign each one a weight based on how strong that association is. Add up a person's variants times their weights, and you get a single number estimating their genetic risk. Kara and colleagues used this exact approach in 2018 and found that 3.5% of the population sits at more than 3 times increased genetic risk for type 2 diabetes, a burden comparable to carrying a rare single gene mutation. And here's the part that doesn't always make it into the headlines, which is 3 different studies looking at type 2 diabetes got 3 pretty different answers. A UK biobank study from Wong and colleagues found an AUC, or area under curve, of just 0.585, which is barely better than a coin flip at 0.50. However, Kara's landmark study found meaningful separation at the extremes, that top 3.5% of the population. But a study in an Indian population by Pemasani and colleagues found a much stronger AUC of 0.795. And part of what explains that is that these scores only capture the heritable piece. They leave out the diet, weight, and activity level, which still drive most of who actually develops type 2 diabetes. The technical challenge with polygenic editing is that you can't just run several CRISPR systems in the same cell and expect them to behave. Guide RNAs crosstalk. Base editors start modifying the wrong site. Cowan and colleagues built multiplexed orthogonal base editors that use RNA aptamer and coat protein pairs like a lock and key to keep each editor bound to only its intended guide RNA. And separately, Wan and Gao built CRISPR arrays that use the cell's own tRNA processing machinery to release up to 31 guide RNAs from a single construct. And both are steps toward editing many diabetes-linked variants at once instead of one at a time. Type 2 diabetes is a strong case study because it's one of the best studied polygenic conditions that we have. It draws on variants tied to how the body handles insulin, how well beta cells in the pancreas function, and how fat gets stored. Kara's 2018 paper found that 3.5% of people carry a genetic risk burden for type 2 diabetes equivalent to a rare single gene mutation just spread across many sites instead of concentrated into one. That's the population polygenic editing is theoretically aimed at. Not at one bad gene, but a whole risk profile built from small contributions. So what would it actually take to lower someone's type 2 diabetes risk this way? Vischer and colleagues modeled exactly that in 2025 and found polygenic editing could theoretically produce large reductions in disease susceptibility. But the word theoretically is really doing most of the work in this situation. This has only been modeled, not tested in people, and it's mostly being discussed for embryos and not in adults who already live with diabetes. Even in a perfect edit, only touches just the genetic piece. It doesn't change the diet, the weight, or the activity level, which still drive most of who actually develops the type 2 diabetes. And ethical considerations is really where the science runs into some real friction. Vischer and colleagues argue that polygenic editing could lower disease risk for the people who can access it while leaving everyone else behind, actually widening health inequality instead of shrinking it. They call for what they describe as a collectivist ethical framework, one that weighs effects on families and society, not just an individual parent's choice. And they also point back to the He Zhengku's 2018 embryo editing case as a cautionary example of moving ahead of both regulation and informed consent. And because the same scoring tools used for disease risk apply just as easily to things like height or intelligence, there's a real risk of sliding from treating disease into selecting traits. So right now, there's a real distance between two things moving at different speeds. The editing tools are still confined to human cell lines in a lab and nowhere near a patient. But polygenic risk scoring itself is already moving into early clinical use for conditions including type 2 diabetes. And that mismatch is part of what researchers like Vischer and colleagues are arguing that the ethical framework needs to be worked out now before the editing side of this technology catches up to where the screening and the scoring side already is. I've listed here the 6 sources behind this week's research, all from PubMed or PubMed Central, very credible, and are all linked with DOIs if you would like to read further. Thank you very much.